Welcome the audience and introduce this technical note on re-sputtering in reactive HIPIMS deposition. Explain that the focus is the pressure-dependent behavior observed in SiO₂/Nb₂O₅ optical coatings. The presentation will connect plasma conditions, ion bombardment, and the resulting net film growth rate. Set the central question: how can process conditions be controlled so that deposition remains stable while re-sputtering is limited? Define re-sputtering as the removal of atoms from a film after they have already been deposited. Emphasize that, in reactive HIPIMS, energetic metal ions, Ar ions, and oxygen-related species can all contribute to bombardment of the growing surface. Point to the highlighted statement: the effective film growth rate is not the deposition rate alone. It is the balance between incoming material and material removed by re-sputtering. Contrast HIPIMS with conventional DC magnetron sputtering by emphasizing its much higher ionization rate. Use the three summary boxes to frame the process. High ionization produces an energetic plasma. The application is a reactive SiO₂/Nb₂O₅ optical stack, and the relevant output is the net rate after re-sputtering is subtracted. Stress that controlling this balance is essential for optical thickness, film density, and overall coating performance. Begin at the target surface. The magnetron magnetic field confines electrons near the target and creates a high-density ionization zone. Then follow the material toward the substrate. Metal ions, Ar ions, and oxygen-related species are accelerated through the plasma sheath, while neutral sputtered atoms also contribute to film growth. The key point is that the film receives both a deposition flux and an energetic ion flux. Their interaction determines how much material remains on the surface. Describe the mechanism as a sequence. First, energetic ions strike the growing film and transfer momentum to atoms at the surface. If the transferred energy exceeds the surface binding energy, some deposited atoms are ejected. This is the re-sputtering event illustrated in the figure. Use the equation to summarize the practical effect. Net deposition rate equals deposition rate minus re-sputtering rate. In SiO₂/Nb₂O₅ multilayers, this directly influences the thickness achieved in each layer. Caution against treating pressure as an independent explanation for deposition behavior. Pressure changes ion energy and ion flux at the same time. In certain operating windows, higher pressure can raise plasma density and ion flux, while additional gas phase collisions reduce average ion energy. Where the increase in ion flux has the stronger effect, re-sputtering rises and the net deposition rate falls. Interpret the pressure trend by considering both variables together. Review the four process consequences shown on the slide: reduced film thickness, optical thickness deviation, refractive index variation, and stoichiometric changes. Explain that these outcomes can accumulate across a multi-layer optical stack and lead to a coating that differs from the intended design. The optimization objective is therefore not simply to select a pressure value. Ion flux and ion energy must be evaluated and controlled together. Close by reinforcing the main conclusion: re-sputtering is intrinsic to HIPIMS and is governed primarily by ion energy and ion flux. Pressure alone cannot fully describe the deposition response. Stable performance requires coordinated adjustment of chamber pressure, substrate bias, pulse parameters, and plasma density. End with the practical takeaway: control ion flux and ion energy together to maintain deposition rate and optical performance.